So her topic is Ratel. MPC is a sidechain, and Yunqi is a PhD student at UIUC, advised by Andrew Miller. And she is interested in system security, peer-to-peer networks, and blockchain technology. So take it away.
Okay, so hello everyone, I'm Yunqi, and today I'm going to present our current work making MPC as a sidechain. So this work is collaborated with Sylvain, he's a software engineer at IC3, and Mikura from HashClock, and my advisor, Andrew Miller. So it is well known that like in most of the mainstream blockchain system, like in Bitcoin and Ethereum, the chain data is replicated and accessible by every node in network. So they will remain public visible forever, which means that if there's a transaction that Bob pays Alice X coins through the blockchain, then every node who has a copy of the chain will know that this transaction happened. This kind of transparency of transaction data is undesirable in specific use case. So there are several work engaged in providing privacy for transactions. The most well-known one is Zcash. Then come with the Monero, Tornado, Cash, and Green and Bean. So they're trying to improve transaction privacy by breaking the on-chain link between the source and destination addresses, make it hard to info users' physical identity from their on-chain transaction history. And some of them also use zero-knowledge proof to hide the payment amount of the transaction. Later on, people further improved the privacy guarantee from transaction to smart contract. With smart contract, blockchain framework become more flexible, and there's more fine-grained requirement in terms of privacy. So a user might want to partial information disclosure so that they only review the result of some functions, but not others. General framework for this purpose can be classified into two categories. One is achieved by zero-knowledge proof, such as Hawk, Zexi, and ZKVN, and another category is implemented by trusted hardware, that is Intel SGX. So ZKP approaches usually work like this. Suppose X is the function to compute, and we want to keep the input data to this function secret. The input data provider accomplishes the computation locally and provide proof to the application operator, which are usually blockchain validators, and the computation is correctly conducted. So the application operators can directly apply the effect of the computation to the ledger after they verify that the provided proof is valid. In this case, the input data remains secret. And the commitment submitted to the chain is critical for integrity reason. When there's a need to review the secret input later, user could not submit another input as it won't be consistent with the submitted commitment. So one use case is of this scheme is on-chain auction. User could submit commitment of their bid before the review phase, and they have to prove that their bid is valid and they have enough money to pay for it. On the review phase, user review their secret input, which should be consistent with their commitment submitted early. And then the application compare the user's input with in plain text and decide who is the winner. So a special property of ZKP is that creating a proof takes a lot of time, but verify a proof is very efficient. ZKP scheme is usually efficient as the application usually has to do the verification, and user can generate their respective proof locally. So the most important use case of ZKP is user identity privacy. With the sender and the receiver's public address remain hidden, the link between the senders and receivers are broken. And the unlinkability plus the pseudo-anonymity of the blockchain could lead to the full anonymity of all the involved parties. And ZKP could also provide some kind of data confidentiality. Input data provider could generate proof for its own secret data and keep those data private. However, there's some fundamental limitation of ZKP approaches. People who generate the proof need to know the entire secret witness. If they are mutually distrustful party who would like to provide secret input to the function together, no one would like to share their sensitive data to others, and there's no way to generate the proof. So the computation capability is limited when using zero-knowledge proof approaches. And another limitation is the data availability. In the review phase, the user who submit the commitment has to be online. So it limits the flexibility of the information disclosure procedure. So we reach out to MPC approaches to overcome those limits of zero-knowledge approaches. We could delegate the whole computation task to MPC service, and the MPC service is run by several MPC servers. Users provide their input in secret form to MPC service, and the MPC servers perform the computation over secret data collaboratively. The benefit of MPC approaches is that it provides full confidentiality and data availability. MPC servers could compute over secret data from different sources, and MPC server can reconstruct the original secret when there's need to do so. It doesn't require all involved users to be present when they want to reconstruct the original secret. And one thing I have to mention is that, like, when we talk about MPC approaches, we only care about its usage regarding to data confidentiality, that is protecting transaction data rather than hiding the identity of participants. The good thing is that we could always patch it with a separate ZKP scheme to provide user identity anonymity. So about when we should use MPC and when we should ZKP and what kind of algorithm we should use exactly. And sometimes we need to use combination of those methods. We build a flowchart to guide ordinary developers when they need to build applications with confidentiality requirements on blockchain. And the flowchart is based on different security assumptions made by developers, whether there's honest majority or malicious majority among MPC servers, and if there's full confidentiality requirements, integrity requirements, and availability requirements. So one direction we would like to extend this flowchart is to add SGX approaches to it. Basically, compare with MPC, SGX approaches have a different trust model. When using SGX, we need to trust the chip manufacturer for security. And we assume that there's no physical attack to the host that running the SGX service. While for MPC, usually we have to assume that majority of MPC servers are honest. Otherwise, we could use dishonest majority MPC protocol, which does not provide data availability guarantee. So back to the comparison between ZKP and MPC, there are some basic principles. When the computation is conducted over secret inputs from mutually distrustful parties, MPC has to be used. And ZKP can only generate, zero-knowledge proof can only be generated when the prover has the knowledge of all the input data, which cannot deal with this kind of situation. And for integrity, it is guaranteed by either the commitment scheme or MPC under honest majority. One would ask, since blockchain already provide integrity according to our knowledge, why do we need additional scheme to guarantee this property? The reason is that if the additional confidentiality layer is implemented by MPC scheme, each server stores their secret shares in their local private database and nothing is stored on the blockchain. So there might be the case that malicious MPC servers alter their local copy and break the data integrity. So thus with dishonest majority MPC, we might need additional commitment scheme to guarantee integrity. And data availability is guaranteed by MPC with honest majority. Dishonest majority cannot achieve it as malicious parties might abort the data reconstruction or refuse to send back their share to the clients, so the clients cannot perform reconstruction locally. And the last one is about performance. As MPC requires communication among most of servers, it introduces relatively high latency. And applications should be able to tolerate this high latency if we want to use MPC to implement it. So in our MPC sidechain framework, we focus on MPC protocols built on top of Shamir's secret sharing. Suppose there are n MPC servers, and each server has a share of a secret input. Only more than threshold number of servers could reconstruct the original secret input. We use a polynomial to create shares for MPC servers, and y-axis intercept is the secret value. The polynomial is of degree t. With more than t plus 1 point, the polynomial is determined and we can reconstruct the secret value. But less than t plus 1 point, the value remains secret. Intuitively, it works like there's a safe box with 3 key holes, and there are 5 key holders. Any three of the key holders could open the box, while less than 3 could not. Since there might be malicious servers who may try to learn the secret without any permission, we do not want those malicious servers break the security of the scheme. Thus, we want the number of malicious servers not exceed T. And at the same time, we want honest server to be able to reconstruct secret without the presence of any malicious server. So N minus F should be larger than T. Therefore, we can get that Shamir secret sharing scheme only works in honest majority setting. With Shamir secret sharing, we can conduct some basic computation. We could use a Lagrange interpolation to reconstruct the secret, and we could also reconstruct secret in batch to save communication time. And linear operation can be performed by MPC server locally. And the multiplication can be performed with the help of the famous liver triples. In order to compute the multiplication of 2 shares, MPC servers need to publicly reconstruct 2 values, which is x minus a and y minus b. So when a user would like to submit a secret into an MPC network, usually we do not let the user create shares of the secret input by themselves and send respective share to MPC servers, because it's not easy for MPC servers to verify that they receive the consistent shares generated by arbitrary users. And they have to make sure every MPC users receive the share before initiating the computation. Instead, we use input mask for users to submit secret input to MPC network. In the pre-processing phase, MPC server generates shares of random field elements, and input mask is actually a random element. Before sending the secret data, user communicate with MPC servers with secure and authenticated P2P channel and request for shares of a random elements, the input mask. Then the user reconstruct the random elements with shares received from MPC servers and mask the secret input X by adding R to it. Then the user broadcast X plus R to MPC network. Each MPC server could calculate its own share of the secret input X by X plus R minus its share of the input mask. So now we can dive into the details of the MPC sidechain framework. In this sidechain framework, we use public blockchain as the coordinator and broadcast channel. User exchange secret information with MPC servers using secure P2P communication channel, and the public blockchain stores all the public or non-confidential information of the application. Clients interact with the smart contract on the blockchain to request the execution of MPC task, and the smart contract logic implements all the access control mechanism, like what computation are allowed and the control flow, like is the secret shared data available and is the computation ready to proceed? By following the instruction from the blockchain, MPC servers engaged in computation over secret data. They also maintain a local copy private database to store secret states of users. So with the public blockchain as a coordinator, the input mask works a little bit different. Before requesting shares from MPC servers, users are firstly required to reserve some input mask on the coordination smart contract. And by calling the reservation function on that contract, the user will get assigned input mask indexes. And then the user requests for assigned input mask shares from MPC network. Once they reconstruct the input mask, the user could publish masked input directly to the blockchain, and which will be accessed by all MPC servers later. So once we know how input mask is achieved in the MPC sidechain framework, we can look into the basic workflow of applications in this framework. Users submit requests to the blockchain with masked secret input and other public inputs. and tell the framework which MPC task the user would like the framework to help it to execute. User submit the request by calling a function of the coordination contract on the blockchain. And if the request is valid, the function being called will emit an event to notify MPC servers to execute the corresponding MPC task. Event contains the required information for MPC servers to conduct the computation. And MPC servers keeps monitoring events emitted by the blockchain. Once they receive the notification, they will follow the instruction contained in the event to carry out the corresponding computation task. When the private computation is finished, MPC server should either report the result to the blockchain if the result should be reviewed. Otherwise, for private result, it is stored. The MPC server stored the share of the result into its local database, and the user who initiated the MPC task or anyone who authorized by the one who initiated the MPC task are permitted to retrieve its private result later. So the main chain basically provides the following functionalities. First is coordinating MPC servers to conduct computation over secret data. Main chain emits event to notify MPC servers to start computation and feed them with required inputs. If two MPC tasks could run in parallel, then main chain will assign different port for the MPC committee so that these two MPC tasks will run on different ports concurrently. And main chain acts as a public accessible bulletin board. Clients post their best input to the coordination contract so that the MPC server could recover their respective share of the secret input later. After each computation, MPC server revealed the public output to the smart contract so anyone can access the result. And the integration of MPC network with blockchain allows us to easily build a incentivization mechanism for MPC servers and allow DeFi project with confidentiality concern being built easily. As for authentication and authorization, blockchain provides a unified identity across the framework. The public key of the user is reused in its private communication between MPC servers. For example, only the user has reserved the input mask K has the right to request for the shares of input mask K, but not anyone else. Only the one who initiated the computation or authorized party could retrieve the private result of a computation. As public data and masked input are posted on the blockchain, it also provides some kind of data backup. The MPC sidechain framework involves program over destroying sections, which including the smart contract on the public blockchain and the MPC framework and the other code to concatenate those two components. So actually, we have to admit that it brings inconvenience for developers. Also, we would like to make it easy for developers who do not have enough crypto knowledge to write their own privacy-preserving decentralized apps. For those purposes, we designed a new language called Ratel, which is aiming to simplify the programming. With Ratel language, developers could write their program in a single common language to program over all these components. So there's a specialized compiler, firstly turn Ratel code into 3 parts, including the Solidity code running on the public blockchain to coordinate the execution of MPC tasks and store public states, and the MPC node, as we use MPC for our MPC backend. MPC code is compilable by MPC compiler. And in the middle is some Python code to concatenate the blockchain part and the MPC part. Python code handles data flow between the public portion and private portion, and it also helps to maintain the local private database, which stores users' private states. Then each part of code is compiled with their specialized compiler. Next, I will explain some code example to illustrate how to write code in Ratel. So each RTL program consists of two portions, the public portion and private portion. The public portion is executed on the blockchain, while the private portion is run by each MPC server locally. Public code is used to provide interface for clients to provide input data and submit requests to run some MPC task. Private code handles retrieving input data from blockchain and run the MPC function and update states and report result after the computation is finished. And the figure shows a secret deposit function, which moves the user funds on main chain to secret account on MPC sidechain. It basically burns designated amount of coins or tokens on the main chain and then mints corresponding amount of coins on the sidechain. So RTL program always start with the public portion, which will be compiled or split into Solidity code. On the left side is the source RTL code, and on the right side is the generated Solidity code. The keyword MPC indicates the end of the public portion, followed by the keyword MPC are the parameters passed from the public portion to the private portion. And those parameters are passed in the form of emitting event. By calling the secret deposit function on chain, if there's no exceptions thrown, it will emit the event to notify MPC servers to mint designated amount of token for the user. And the code block led with keyword MPC are private portion. The private portion consists of two parts, MPC code and Python code and the Python code to concatenate the execution of public code and MPC code. MPC portion begins with the keyword MPC input and ends with keyword MPC output. Since we are using MPC as our MPC backend, the input and output of MPC function are passed through input and output file. The code of reading input from input file, writing output to output file, and necessary type conversions are automatically handled by the RTL compiler. And the last portion of the compiler code is Python code. This part of code includes receiving instructions and input data from the main chain, prepare input data for MPC function, and update both private and public states after the computation is finished. Except for input fetching from main chain, some input data to an MPC function are private states stored on local database. Each MPC server stores a share of the state so that they cooperatively maintain the private states for users. After the computation, Python code handles writing back updated private states to its local database. And if the result of the function is allowed to review, MPC server will reconstruct the result and post it on the blockchain cooperatively. With the existence of malicious server, majority of MPC servers need to approve to upload a value to the blockchain. So the code of this voting-like process is also automatically generated by RTL compiler. And RTL also provides convenient way for user to pass secret input. Secret data field is marked by a $sign. So right now we support secret integer and secret fixed point number. Developers only have to mark data they would like to make it secret, and the RTL compiler will handle all the input mask stuff for them. In the public portion, secret fixed point number amount A in this trade function is automatically interpreted by the RTL compiler. It will compile it to input mask index and the value masked by the input mask. So users should reserve input mask they need to use in advance by calling the function beforehand, and the contract will check the ownership of the input mask. Secret data is not allowed to be operated in the public portion. And when amount A is passed to private portion, that is the Python code, MPC servers recover their respective share of the data with their own share of the corresponding input mask. Once the input mask is unmasked, they are allowed to engage in addition in Python code and kinds of computations supported by MPC's compiler in MPC code. As for the type conversion between Python code and MPC code, it is completed by specifying the data type explicitly in the MPC input and MPC output part. So we have implemented several applications with this framework. So the most important application we implement is the HoneyBadgerSwap. So it is an automatic market maker with additional confidentiality guarantees. We run a live instance of this prototype for months and publish a blog post about it. So we want to show that even though MPC usually has a relatively high communication cost and makes it unsuitable for expensive computation, it can indeed be a practical system. So since Uniswap is a lead market, where all the information about trades are public visible, as previous orders would move the price of the market, the sequence of the field orders will influence the actual closing price of the asset. So Uniswap is usually vulnerable to front-running attacks launched by block miners. So in HB swap, the exact size of liquidity pool and the volume of trading remains hidden. Since the details about each order is unknown to exchange managers and miners, they could not launch front-running attack to reorder user request and make profit from it. So in HB swap, you could move your fund from main chain to your secret account on the MPC sidechain, and the balance of your secret account is only known by yourself. And you can add liquidity to the pool and submit trade to Uniswap, to HB swap, sorry. The amount of trades and liquidity operations are secret. So this is how our front end look like. And by clicking the deposit button, you can move your funds from your personal account to the smart contract and then to the MPC sidechain. And you can init a new pool and add liquidity to existing pool and remove your liquidity from the pool. So here's the page of a trade you will look like. Similar to adding liquidity operations, the amount of trades are secret. So you will need to use input math to obfuscate your trading amounts. And the states here shows the current state of your operations, whether it's ongoing, failed, or succeed. In HB swap, we only review the average price of last batch of transactions. So the price shown on chain is just an estimation, and you can set slippage tolerance. If the price has slipped beyond this limit, when your trade is actually executing, then the order is canceled automatically. So there are some challenges which we are trying to tackle right now for the MPC sidechain framework. First is to improve its performance by adding concurrency. And each MPC task is basically consists of reading states from the local private database, compute function collaboratively, and update local database. So for two MPC tasks, if they're accessing different field of the database, they could be executed concurrently. And another aspect is about fault tolerance. Basically, we're talking about crash fault tolerance here. Different from other MPC framework, which usually focus on how to carry out independent MPC tasks. In MPC sidechain, MPC servers maintain their local private database. When the crashed server come back online, how to sync states, updates happening when it's away, and how to make use of blockchain as a natural place to put checkpoints remain as a problem we need to solve. Yeah, so
30-second warning.
Yeah, okay. I will end my presentation by this figure created by Andrew. So our MPC sidechain might fill the gap by providing both programmability and full confidentiality. Thanks.